Today we will be discussing about a linear antennas. In the linear antennas, we will discuss about three types of antennas or three categories of antennas will be under discussion. Up to now, what we have done is we have seen what is Hertzian antenna and the science part of Hertzian antenna. Today we will discuss the technology part. So linear antennas from an engineering perspective or from a technician's perspective, we will consider linear antenna. Now what is meant by linear antenna is the extension of antenna is linear, which means the physical construction of antenna is such that the antenna is in one line. So total physical appearance of the antenna is along one line. In all other direction except that line, in all other direction, the dimension of the antenna is negligible. Then we call it a linear antenna. Now suppose we are going to consider a linear antenna. Linear antenna should always be of finite length. It should not be of infinite length. So its length is finite. It can be very small, extremely small, but the length should exist. It should be finite. It cannot be infinite. Now assume that this linear antenna is oriented along a line which is along the z direction. So if the line is along the z direction, then we also say that the antenna length, total length of the antenna is L, and the antenna is symmetrically placed about the origin along the z direction, which means from the origin, if we look along the z direction, it will be L by 2. If we look along the negative z direction, it will be up to minus L by 2. So extension from origin in the positive z direction is L by 2, in the negative z direction is minus L by 2. And the current on the antenna, since the antenna is along the z direction, the conductor antenna is a conducting body usually. Since the conductor is along the z direction, so the current also will be along the z axis. If the current is along the z axis, then surrounding the current there will be a magnetic field. You know, if there is a current is surrounded by the magnetic field. So if the current is along the z axis, use your right hand rule. So extend your thumb along the z axis, curl all the other fingers, and then that gives the curling of your fingers gives the magnetic field. So the magnetic fields will be surrounding this antenna. They will be symmetrically around the z axis. So the magnetic field will be completely symmetric with respect to z axis. If the magnetic field is completely symmetric with respect to z axis, then the magnetic field will be a function of theta only. If it is symmetric about the z axis, which means it is not varying in the xy plane. In the xy plane, everywhere it is same, which means there is no phi variation. Phi is the angle from x towards y. Therefore, there is no variation in phi. So it is constant with respect to phi. The variation is only with respect to theta. Now let us make the assumptions for this antenna. The first assumption is antenna is linear. We have already discussed. Second assumption is it is along the z-axis. That I have already discussed. Extension is from minus L by 2 to L by 2 along the z-axis. So in the negative z direction it is at minus L by 2, it ends at minus L by 2. At the positive z direction it ends at plus L by 2. Now that also has a physical significance. What does it physically signify? Now when you go to minus L by 2, beyond that there is no conductor, so therefore beyond minus L by 2 there is no current. Similarly, when you come to L by 2, beyond L by 2 there is no conductor, therefore no current. So current is confined between the range of Z, which is between minus L by 2 to L by 2. Or you can say minus L by 2 less than equal to Z less than equal to L by 2 is the range where there is current, and the current is varying as a function of Z. Since the antenna is oriented along Z axis, current is varying as a function of Z only. Therefore, we will say that the current density on this infinitely thin conductor or thin antenna or thin wire, it is a wire if you call. So on this infinitely thin wire, and the current density Jr is equal to Z cap. Current will be oriented along Z direction because the antenna or the conductor is along Z direction, so the current will be along Z direction. So therefore, and current is a vector quantity. So therefore, current density is a vector quantity. Therefore, Jr will be Z cap. That gives you the unit vector of the current density. Then Iz is the variation of current along Z. Then Ix. Now Ix here will be delta X because along X there is no variation, as the antenna is not extending along X. It exists only at X is equal to 0. So Ix will be delta X. Similarly, Iy will be delta Y. So Jr is equal to Z cap Iz delta X delta Y. So these are the assumptions. With these assumptions, we will consider different types of antennas. Now in these assumptions, the last assumption is Jr, which is Z cap and Z cap Iz. So what will be Iz? The Iz can take different forms. The Z variation will be different forms. So that each form will be represented by a function. So those functions are Iz is equal to I L delta Z, which means I is the current, L is the length of the antenna, delta Z means it exists only at Z is equal to 0, otherwise the current is 0. If that type of current distribution is there, then we call it a Hertzian dipole. The Hertzian dipole is actually a uniform line element, and a small linear dipole example do not satisfy on the Helmholtz equation. This Hertzian dipole is a very small antenna. It does not satisfy the Helmholtz equation. Similarly, Iz is equal to I. So throughout the wire, throughout the antenna, current is I, except at its end. So that you can say Iz is equal to I for minus L by 2 less than minus L by 2 less than Z, less than equal to Z, less than equal to L by 2. That is Iz is equal to I, otherwise Iz is equal to 0. If that type of distribution, current distribution is there, then we call it an uniform line element. if Iz is equal to I into 1 minus 2 absolute Z by L, then we call it a small linear dipole antenna. Now what is this? I is the peak current in the antenna. Then 1 minus 2 absolute Z by L. Now suppose Z is equal to minus L by 2. Then absolute Z is equal to L by 2. So 2 into L by 2 by L. 2 into L by 2 is L. L by L is 1. So 1 minus 1 will be 0. So when Z is equal to minus L by 2, it is 0. Similarly, when Z is equal to L by 2, it is 0. In between, it is from -0, it is increasing. When Z is equal to 0, so if you put Z is equal to 0, absolute 0 is absolute Z is equal to absolute of 0. So the second term will be 0, it will be I. So it goes from 0 to I linearly, it linearly increases 1 minus 2 absolute Z by L is a linearly increasing function. So it increases linearly from 0 to I, then decreases linearly from I to 0 to the other end, which means it is like a triangle. It is a triangular distribution. This distribution, if you have a triangular distribution, these are called small linear dipole antennas. Then the most common one for linear antennas is called the standing wave antenna. For the standing wave antenna, Iz is equal to I sin k times L by 2 minus absolute Z. Now suppose in this case also Z is equal to minus L by 2. If Z is equal to minus L by 2, absolute Z is equal to L by 2. So L by 2 minus L by 2 0, sin 0 is equal to 0. Then Z is equal to plus L by 2 again will give you sin 0 is equal to 0. So Iz will be 0 if Z is equal to plus minus L by 2. In between it will vary. When Z is equal to 0, it is sin k L by 2. Now k is equal to 2 pi by lambda. So this will be sin 2 pi by lambda into L by 2. So or sin L pi by lambda. So Iz is equal to I sin L pi by lambda when Z is equal to 0. Then the next one is the half wave dipole antenna. For the half wave dipole antenna, it is like a standing wave antenna, but you just put L is equal to lambda by 2. Lambda is the wavelength, free space wavelength. So lambda by 2 is half the wavelength. Since L is equal to lambda by 2, half the wavelength, therefore we call this half wave antenna. So if we put L is equal to lambda by 2, Iz will be I sin k lambda by 2 minus Z. When Z is equal to 0, this will be k 2 pi by lambda into lambda by 2. So just put that 2 pi by lambda into lambda by 4. So that will give you 1, sin 1. Sin pi by 2, that will be equal to 1 peak. If you put L is equal to lambda by 2 in this form, Iz is equal to I sin k L by 2. So for L you put lambda by 2, then it will be lambda by 2 into 2 pi by lambda. So 2 pi by lambda into lambda by 2. Lambda cancels, 2 cancels, sin pi. Sin of pi minus Z. Sin of pi minus Z is equal to cosine Z. So you will get a cosine function here. So this cos kz will be same as that. Then you know a traveling wave is given by exponential minus jkz form. Therefore, if the distribution is of the form I into exponential minus jkz, that is called a traveling wave antenna. So these are the antennas. These are all linear antennas. There is another type of antenna which is of interest, which is called the loop antenna. In the loop antenna, we assume that there is a loop in the XY plane. There is a loop on the XY plane and it is placed symmetrically around the Z axis. It is in the XY plane symmetrically around the X axis, which means its center is at origin O. Now this antenna is infinitesimally thin as in case of linear antenna, and the current will be now azimuthal. It will be in the XY plane varying along phi. So current will be azimuthal along this. Current density on this using cylindrical coordinate system rho phi z will be equal to the current density will exist on the OR, which is at a distance A from the origin, and beyond that there will be no current. So therefore it will be delta rho minus A, that is 1. Then along Z there is no extension, so delta Z. So on those two are gone. Then the current flowing on the AR is I. So I, then the current direction is phi cap. But we are not going to consider the loop antenna or all the antennas that I discussed now. We will be considering very limited number of antennas. Let us look at those discussion, those limited number of antennas. So first we will start with Hubble dipole. Now for the linear antennas, we will consider first the radiation vector for a linear antenna. Forget this red line. Let us that we will use later. But for the radiation vector, we know now the current is along the Z direction. So since current is along the Z direction, therefore the radiation vector F, if you remember, the radiation vector comes from the vector potential. So the radiation vector F will be same as vector potential. Vector potential will be in G direction because current is in G direction, and from the vector potential we find out radiation vector. Vector potential is found by integrating the current with the exponential minus jkr. So therefore on the radiation vector F will have only a Z component. So it will have only Z component, it has no XY component. So if it has only G component, let us see how it will have only G component. F is equal to integration J R dash exponential jk dot R dash integration over the volume. This is the definition of F that we have already seen. Why we are taking R dash or R prime? Prime indicates that the integration is over the source position vector is given by primes. Now that we will write as, if I expand that, k dot R dash is equal to k is equal to x cap kx plus y cap ky plus g cap kg. Similarly, R dash is equal to x cap plus y cap plus g cap. So if you take their dot product, so that part will be exponential j kx x dash plus ky y dash plus kg g dash. Then j, we have already seen for the linear antenna, the distribution j is z cap I g dash delta x dash delta y dash. Now this is, and it is a volume integral, so dx dash dy dash dz dash. Now along dx and dy there is no variation. The variation is delta x dash exponential jk x dash dx dash. That is for the x integration. X dash integration, the term to be integrated is integration of delta x dash exponential jk x dash dx dash. Now using the Dirac delta function property, as you know, fx delta x dx integration is equal to f0. So here fx is exponential jk x dash. So on that we will put exponential jkx0. Now exponential jkx0 is equal to exponential 0. Exponential 0 means it is equal to 1. E to the power 0, anything to the power 0 is 1. So exponential 0 is equal to 1. Similarly, for the y component of integration, it will again be 1. So if these two are 1, then the integration now becomes, and now the integration is trivial in x dash and y dash. We have got it is 1. It extends over the antenna length L for z dash, integration over z dash, it extends over the antenna length. Let us take a break. There is some disturbance.